Thank you for coming to my talk. My name is Fangming. I come from the Institute of Information Engineering CAS. This is a joint work with the Institute of Computing Technology CAS and the Sangfor Technologies Incorporation. Today, I'm going to talk about detecting data race vulnerabilities in COM objects. Considering time limitation, I will show the general idea of our research, and you can find more details in our paper. COM, which is short for Component Object Model, is a binary interface standard for developing software components introduced by Microsoft in 1993. With the rapid growth of the Microsoft ecosystem, COM becomes a foundation for many key Microsoft technologies. COM objects are now widely deployed in the Windows operating system's user space, from Office to ActiveX objects in browsers to DirectX and the user mode driver frameworks. COM objects are widely used in Windows runtime and system service components, providing service for user applications at high privileges. COM gives the power to activate and invoke COM object methods via predefined interfaces through COM runtime and the binary protocol, in which breaks the limitations and the invoker and service provider need to stay in the same process. COM provides threading features, multi-threading features that calls from different clients to the service object interface methods may run concurrently. COM objects use the threading model named apartment, which is a logical encapsulation to specify thread sharing rules for COM objects. The left figure shows the threading model with process boundaries. There are three types of threading modes in COM. First is single-threaded apartment. A single-threaded apartment consists of exactly one thread. A COM object in an STA can receive interface method calls from the only thread in an STA. Second is a multi-threaded apartment. A multi-threaded apartment consists of one or more threads, just as the top right corner of the picture shows. Each client request will be served with a new thread in the privileged local process. Consequently, data races may trigger if the interface methods are not thread safe. These data races often lead to memory corruption bugs such as buffer overflows and user after freeze. Attackers can easily exploit these bugs to gain escalated privilege or execute arbitrary code. Third is a neutral threaded apartment. The neutral threaded apartment is introduced for more efficient cross-apartment calls. Similar to MTA, COM objects in an NTA need to guarantee thread safe by themselves. Our research found out that MTA and NTA COM objects are prone to data race attacks if thread safety is not guaranteed. We demonstrate the real-world data race vulnerability in geolocation COM object, which is acting as a system service object running inside the service host process. The left picture shows the decompilation code of two interface methods of the object. The interface method PoC3 and PoC6 introduce two high-impact vulnerabilities of the object. As the right figure shows, if the client invokes method 3 and 6 concurrently, since PoC3 and PoC6 are methods of the same object geolocation, line 3 of PoC3 and line 20 of PoC6 operates a similar variable. The former is read out and the later is write to. In the meantime, PoC6 frees this plus 104 at line 18, which results in a possible use after free vulnerability when invoking PoC3 and PoC6 concurrently. Similar things happen when clients invoke PoC6 alone. If one free operation at line 18 happens before another free operation in another service thread, a double free will happen. The two circumstances both lead to privilege escalation in this scenario. In order to effectively detect data race problems in the large size of COM binaries in the underlying system, we propose a static solution named COMRace. COMRace solves the problem in 4 steps: extract COM objects, uncover interface information, identify unsafe methods, and synthesize PoC exploits. Firstly, we extract COM objects information and store them locally, which is a basic step of the solution. COM objects register themselves under the Windows registry path HK class's root class ID with a unique CRS ID, so we can extract information needed from the registry. COMRace extract COM class information, including basic information, then it extracts service information and service information. After this step, COMRace gets registered COM's class name, thread model, binary location, service permissions, and so on. After extracting the information of COM objects, we dig into the COM objects implementation binary to uncover interface implementation. COM exposes interface implemented in its corresponding binary file. The implementation of an interface method has exactly the same type signature as the interface declaration. Firstly, COMRace needs to retrieve the interface declaration from binary files. This process is completed with the help of OIE-view.net. The decompiled geolocation interface is shown as the right picture. Secondly, in order to locate the right implementation of the COM object, we need to reconstruct the table information from the binary. The V-table reconstruct procedure relies on three key observations of the Windows binaries. We use observations and heuristic rules for guiding V-table reconstruction procedure. After uncovering the V-tables and interface declarations, we try to find the V-tables and implement all declared interface methods. This can be challenging since we lost method names and user-defined structure information. For every V-table candidate, we firstly examine the parameter type and the interface layout consistently, after which candidate list is shrink to those interface has inheritance relationships with an interface inheritance check to select the corresponding V-table, which indicates the corresponding interface implementation. Now we have the corresponding implementation of each interface methods. We can identify unsafe methods. An interface method is regarded as unsafe if it can access member fields without its synchronization. Hence, we examine every instruction in an interface method, as well as its calling methods, to check whether there exists an unguarded field access or not. This is realized by tracking the usage of this pointer, since all member fields are accessed via this pointer with a constant offset. This module reports all unsafe methods and unguarded field offsets with 6 types: read-read, read-write, read-free, write-write, write-free, and free-free races. An example of the analyzed field usage and field types for interface method of geolocation is shown at the right picture. The most important part of our algorithm is processing virtual method invocations. We apply the type propagation method and the track field usage to resolve a virtual call target given the type of the member field. And then we conduct a case analysis for each instruction. We define a sync variable to count the number of synchronization operations to check if lock and unlock operations are balanced. We also apply the list of predefined free and synchronization APIs to track the sensitive free and lock unlock operations. For more details, please refer to our paper. In order to verify the output of identified unsafe methods, COMRace appends a module to try to synthesize PoC exploits automatically. The PoC synthesize are built on a predefined PoC skeleton program. This is because the PoC programs share a similarity to a certain extent. A manual program for the example CVE is shown at the right picture. The PoC skeleton program uses a pre-defined generated header file to complete the variable definition part as the first red cube. Now the key problem is now how to prepare parameter values for the interface method. For primitive values, we set random chosen initial value. For interface typed value, we traverse interface dependency graph to generate a sequence of method calls to get the interface typed argument instance. Then, after the PoC program compiled, we run the PoC program concurrently with PHP enabled and collect the runtime information. Evaluation. We evaluated the effectiveness of COMRace on Windows operating systems and the React OS system, and we designed several experiments to answer the following questions. Question 1, how effective can COMRace analyze commercial off-the-shelf COM binaries? Question 2, how effective can COMRace detect unsafe interface methods in COM binaries? And are they prevalent on the Windows platform? Question 3, how dangerous are those data race bugs and can they cause severe damages? Question 4, how precise is COMRace in detecting unsafe interface methods? For the first question, how effective can COMRace analyze commercial off-the-shelf binaries? Among the total COM objects on Windows 10 platform, COMRace successfully analyzed 10420 of them with a success rate of 92.1%. More than 80,000 of the analyzed COM objects support MTA or NTA threading model. 463 among them are cross-process COM objects, which are prone to data risk attacks. Each COM class consists of 8 member fields on average. Question 2. For question 2, how effective can COMRace detect unsafe interface methods in COM binaries, and are they prevalent on the Windows platform? As for our experiment results, 62% of the valid PoC programs can trigger memory question bugs. Unsafe methods and unsafe COM objects are prevalent. 18.4% of total methods and 38% of total objects, suggesting widely existing data risk bugs. Our experiment demonstrates that those unsafe methods are highly possible to trigger runtime bugs, and some can result in serious security violations. Question 3, how dangerous are those data risk bugs and can they cause severe damages? All the 26 confirmed vulnerabilities can lead to privilege escalation. 23 of them can be exploited to escape the sandbox security boundary imposed by the Windows application container. More importantly, in 20 vulnerabilities, the sandbox privilege can be exploited to anti-authority system. This suggests that an attacker can gain unlimited privileges from those PoC exploits, posing serious security threats. Question 4. How precise is COMRace in detecting unsafe interface methods? We evaluate the precision of COMRace on the open source React OS platform. Results show that COMRace can successfully extract all 147 MTA COM objects out of 434 total COM objects from 100 binary files and recover 152 out of 172 interfaces. We failed to recover 20 interfaces because COMRace cannot locate the binary file implementing those interfaces, although they are declared in the ideal source files. Manual inspection indicates that they may not public accessible. COMRace reports 19 unsafe COM objects with 51 unsafe interface methods. These are 16 false positives with a false positive rate of 31.4%. Conclusion: we present COMRace, the first database vulnerability detection tool for COM objects. The solution applies static binary access to detect unsafe methods from the off-the-shelf binaries, then verify static analysis results with synthesized PoCs. Experiments show that unsafe methods and unsafe COM objects are prevalent on Windows. COMRace automatically synthesizes 234 PoCs from 82 unsafe methods. 145 PoCs lead to critical memory corruption, exposing 26 CVEs. This is for my talk. Thanks for listening. Questions are welcome.